All right, everyone. If we could calm down a bit, we will go ahead and get started with the Spring 25 ACM Cyber Cross AI Symposium. So just quick overview, as per usual. The symposium is just our celebration between both ACM Cyber and ACM AI, highlighting all of the cool things both clubs have been doing over this quarter. Thank you so much for coming. We hope you have a lot of fun and maybe learn a thing or two about stuff both in your club or in the other club that you are not part of, or if you're not part of either club, from both.
All right, so first we just want to give a shout out to a bunch of our guest speakers that joined us this past quarter. So at our comp bio panel, we have Professor Ernst, Professor Shu, Paloma, and Alexander, and they all were able to provide some good insights on the field of computational biology. And then also at our mini ML challenge, we had Professor Kadambi and Spriha Deshpande. So we just wanted to give a big thanks to them, even though they're not here. We want to recognize what they did for us.
And then we'd like to thank Professor Nader, Professor Tien, and Professor Kumar. Professor Nader, he's been pretty involved with the ECTF team. We're very grateful for him lending us the Chip Whisper, Professor Tien advising TBR and letting us into the room. And yeah,
Yeah, so a brief introduction to both AI and cyber. So who is ACM AI? We're the largest AI and machine learning club on campus, and we host workshops and projects and have Kaggle competitions. So we have capstone and research track and workshops, which are weekly meetings for everyone to learn machine learning theory. And these mainly run in fall and winter. And our projects track was our main event this quarter, which are quarter-long projects where members build large machine learning models from scratch and in small groups and have different projects with topics like generative vision and NLP.
Yeah, so about ACM Cyber, we are the largest and probably only cybersecurity club here at UCLA, and our goal is to make cybersecurity simple. And we do this through a couple of our tracks, Cyber Academy, where we teach the basics to cybersecurity to anyone interested. Cyber Lab, which will also group ECTF into, where we get to work on some pretty cool cybersecurity projects in groups. And Psi Beta Rho, our competitive cybersecurity team, which is currently number 3, but I think as of like winter, we were number 1. So, we'll get back up there. Yeah, and this is just going to be our rough agenda for our teams. Just keep this in mind so you know roughly when you're going to go next.
yeah, and if you've been to our previous symposiums, you'll notice that we have dinner at the end this time because we can't eat inside Hmong. So yeah, if you want food sooner, like make your talks, speedy.
Yeah. Without further ado, let's get the R1 group from AI up here. And yeah, we only have one mic, so you'll just have to pass it around.
Introduce us, sir. Oh, okay. Hello, everyone. We're the R1 project, and this quarter we kind of tried to re-implement R1 from DeepSeek, if you've seen it, and our slide also has DeepSeek in Mandarin. I'm Leon, by the way.
Hi, I'm Ryan.
I'm Daniel.
I'm Jackie.
And I'm Ben.
All right, so first off, the main idea behind R1 was chain of thought, and it's a different way of generating outputs. So when you generally think of LLMs giving responses, they'll just take in the input, do some like complicated matrix multiplication behind the scenes, and then give you the output. But you have no real way of knowing where it went wrong. So with chain of thought, what you get is these sort of reasoning traces where you can see how the model thinks and how it gets to its answer. And even in the original paper, they were able to get the model to revise its answer if it was wrong.
The main technique we use for rewards is GRPO. Before they use PPO, which uses a value model to help determine basically the advantage, given an output, how good it is relative to other outputs. But GRPO just kind of gets rid of this value model entirely. So it just groups several outputs and determines from this group of outputs which is better, and then tries to essentially tune the model to make these better outputs more probable. So what prompt we actually use to train to actually fine tune our model is here. We'll talk about the data set in a bit, but then the main thing we really used was we included think tags to have the model basically note when it's thinking, showing its thought process, and answer tags basically show what it's meant to output, and a box tag which actually for us to determine what its actual output is. Specifically, we're using it for multiplication, so thinking would be like it doing its computation, and the box tag of the box would simply just be the output.
Okay, about the data set, funny story, we actually start with like a mathematical computation questions. Then we realized our model was like too dumb to do that. So then we start with something easier, like a multiplication. So we start with like a single digit multiplication, and then we move to the 2 digits one. Okay, so this is actually the model we use is it's like it only has like 7 billion parameters, and I think compared to all the other like large language model which hundreds or trillion level, so it's not performing good. And because our GPU only have 24 data byte RAM, and even we use half like a precision, like 16 bytes for each parameter, it almost take all of like RAM.
So I'll talk a little bit about the things that went wrong. We had a few roadblocks in the early and I guess also the later weeks. The first issue we ran into was that the model learned to output nothing at first, so we were really confused. We thought it wasn't training properly, but then we found out there was some issue with the repetition reward, such that the model was being punished for longer responses, so it essentially learned to not output anything. And then we had a few issues with like things not being compatible with what Hugging Face was looking for, which is really annoying. The first thing was our data set formatting. I think it like Hugging Face was expecting 2 specific parameters called completions and label, and our data set basically wasn't using those names, and the tokenization was also wrong. And the last thing we ran into is that this one was my fault. I wrote a regex to basically like judge whether the response was right or not. And the regex would basically look for the latex box, and I was assuming there was only one instance, which would be the final answer, but it turns out that the prompt itself also has box in it. So we were just basically it would always return that the model was wrong.
Okay, so if you're familiar with Hugging Face, you might be thinking, okay, so we use TRL. That's pretty easy, right? Wrong. We actually probably shouldn't have used Hugging Face because we ran into several more problems with just Hugging Face itself. For example, the docs are completely poorly maintained. Like a lot of the parameters aren't even there, and some of the parameters that are on the TRL docs aren't actually implemented in the model. So we spent several like half an hour trying to figure out why we couldn't do like gradient clipping, because it said we could in the docs, but it didn't actually work in our model. gradient accumulation, which we tried to use to improve our memory performance, really just would not work, even with like lots of random magical functions we found in Hugging Face. It's also not very well documented. And then we also had some really weird model outputs at first. We thought our model was not working because even though we had like an increasing reward, somehow Hugging Face always output 0 loss like at each training step. And we just assumed that meant like, okay, our model's not actually training because it has 0 loss. Well, it turns out that for GRPO TRL, it's actually normal for it to have 0 loss. It just doesn't use that parameter and it still outputs it for some reason. So we spent a long time on that, like about a day trying to figure out why that was the case until we found this small part of the documentation. So we hated it so much that we used AI to generate evil pictures of Hugging Face. So here's Hugging Face, but evil. Another picture of Hugging Face, but evil. And moving on, we have another picture of Hugging Face. But actually, we'll go on now to another picture of how much we hate Hugging Face because this was a really annoying library to work with. We probably should have just unrolled it. Okay, so the part we're all waiting for, the results. So our reward was pretty good. It kept on increasing. We didn't actually include a graph of it, but trust us, please. The base model got like about a 10% accuracy. So like, the final data set we settled on was like, it would generate like 2 random numbers between 50 and 1000 and then try to multiply them together. So Quen 7b was not very good at this, getting only about 10%, but after about 250 training steps, we managed to get 27%, which sounds pretty bad because a human can do this with about 100% accuracy given enough time. But, it's a large language model, so, we're improving it a little bit. And yeah, I think we're pretty happy with these results. Thank you. Any questions? Yes, in the back. Yes.
Like making sure it boxes the
Yeah, so originally we did want to do like I think the cold start you're talking about is R10, right? We wanted to implement that one first, but we were having like some issues with like actually training that model. When we were talking about earlier, like the issues with like the slash box, we actually originally thought that was because of the cold start. And it was just like not, it was like learning to output gibberish while it was like doing the box. It turns out that was actually an issue with our tokenization in the end, but we like, because we like scrapped that initially, we just went directly into like the like curriculum learning. So yeah, we didn't actually implement that. Yeah, thank you guys for your time.
Right, if we could have Burp Suit Lab come up now. And let's give them a round of applause.
Hello, this is the Burp Suite Lab.
So for this quarter, what we did was we wanted to make our own burp suite. And what does burp suite do? Well, it's kind of like this application that you can use for web security. And so one of the main features is that it's able to intercept HTTP requests between a browser and a server.
And then, so for some of the malicious things you could do, you can just, since we already intercepted, we can just modify it, tamper with it a bit, change a few values. And then we get responses that we're not supposed to get. We can also dictionary attack and brute force attacks to figure out things that we shouldn't normally be able to find when we're working on this website properly. And we can also scan a website for vulnerabilities.
Okay, so for our project, we also created some UI to be able to use the project. Nicely, now we didn't get to finish the UI, but we did make some good progress on it. So you're brought to the home page and you can click the intrude or race condition buttons, and supply an HTTP request template, parameterized with a word list that you can choose. And then this just allows you to easily perform your desired attack.
Okay, so one type of attack we did was a door busting attack, which is directory brute forcing. We did this by using word lists to uncover hidden and unlinked content with common directory names. So we would send HTTP requests to a server, and then using the base URL, we would recursively add words from the word list and see if the request sends us back an interesting response. And if it is, then if like a directory is found, then we can recursively search deeper for the attack.
So we also tried to exploit race conditions. So here we have like a classic bank example. So you have an account with $100 in it, and then you make 2 requests for $100. What should happen is it should go in order. So for the first request, you check if there's $100, that's true. You just send that and update the balance to 0. And then when the second request arrives, it should see that there's $0, and so you shouldn't send $100. But if there's a race condition, what's possible is that the checks if there's 100, they both return true. And so you send 100 2 times, and the balance is just 0 at the end, and you get more money.
Okay, so the first race condition attack we did was on HTTP1. To do this attack, we first open parallel connections using threads and send most of the GET requests on each connection. Once we got through all the requests, we send the remaining bytes of the packets on the connections. And because these packets are small, it reduces network jitter and has a higher chance of arriving at the same time.
So we then implemented the single packet attack on HTTP2. This is different because HTTP2 is multiplexed, so it can support multiple requests in the same connection. So instead of sending the last bytes at the same time across different threads, like we did in the HTTP1 attack and the HTTP2 version of this attack, we carried it over a single TCP connection. So this attack sends most of the data of each request first through packets, and then stores the last data in one packet and sends it at the end, which guarantees requests complete at the same time.
Yeah, so that's it for our Berkeley lab.
Next, we'll have the tuning transformers group, if you want to come up here.
Okay. So, do you want from on that side? Oh, okay. So first, I guess we can just start with like, what's a transformer? So a transformer is basically like an architecture for LLMs where you take like text and you sort of turn it into numerical values like embeddings based on the content. And then you use a bunch of sort of different processes like attention and then other processes like dropout if you want to make it a little more accurate to understand the relationships between words. So based on that understood text, the LLM can then begin processes to sort of create like a response or output based on what it understands in sort of separate processes. You can see like that picture right there. So what we primarily focused on this quarter was tuning transformers. So because transformers can deal with a lot of different sort of large amounts of input and whatnot, it's can be very sort of time and energy costly to go through and change all the different sort of values and embeddings when you want to train it. So by tuning transformers, you can take existing models, or you can train existing models on more specific data to allow it to be a little more accurate and a little bit more tailored depending on what system you want it to perform, without having to retrain all of the other different sort of like, parameters and whatnot.
All right, so we worked on retrieval augmented generation. So what exactly is retrieval augmented generation? The idea is that the user will submit a question or a prompt, and then based on the question or prompt, a nearest neighbor is searched on some document, and it looks through the document and it tries to find the top K like passages that are most relevant to your prompt. And then so what you do is then you take that question along with those top K passages as context, and you pass them along to a large language model, and then the large language model answers the question and provides an answer. And the applications of RAG, the reason why RAG can be useful is because it's really good at handling very large documents. So if you have very large or like dense documentation, you can use this technique to get like quick answers if you need it. And yeah, and then RAG can also have its own limitations. For example, LLMs have very limited context windows. So it can be very hard for it to sort of pair the question with the context, and thus it can give not good answers, which we will see in the next slides.
So here is the project that we did on RAG. So the data set we gave it is the UCLA General Catalog from 2023 to 2024, which consists of all of the UCLA courses. And the idea is that we can ask any question from about the UCLA courses, and it's going to give us a somewhat valid response. We do the embeddings. The large language model we use is Gamma 2B because it's free. And the responses are okay. In the code here, the question that we ask is, what is Introduction to Computer Science 1, which is CS31, and it answers, it's a 4-hour lecture that covers some of the basics of computer science, blah, blah, blah. Topics covering the course include data types, control structures, and algorithms, which is what's in the catalog. Oops. Spoilers. There you go. Yeah.
Right, so from our results, what we got were that it low-key gave some good answers on very specific problems. Like for example, that one we just showed where we asked it, what is Introduction to Computer Science 1? And it correctly returns CS31. And it's pretty good at extracting relevant passages. But there were a few cons, like for example, in this question, how many courses are offered at UCLA, which is clearly in the information that we provided, but it requires a little bit more thought because you have to look at more parts of the document. And because of that, the RG answer is the context is not specified the number of courses offered at UCLA because it's not explicitly said. So this is a bit of a problem. And also another thing that we found is that sometimes we actually got better answers on questions without context by literally just feeding it to a large language model. So that's a definite problem with our RAG implementation. But where there are lots of ways that we can possibly improve it. Number one is that we could figure out a way to get smarter embeddings, because the way that we did embeddings is very rudimentary. So if we did better embeddings, then maybe you get better results. A better model, because the one we used was very free because we were poor. And then also another thing we could have done is we could have used multi-head attention. And those are possible ways that we could improve our implementation. And for your enjoyment, we have a Lord of the Rings meme. Yeah.
So we focused on the other aspect of tuning transformers, which was a LoRa or a low rank adaptation. So LoRa is an efficient and lightweight method for fine tuning pre-existing language models. It basically helps you train with less data, prevent overfitting, and it's just overall less complex and much more efficient. Basically all you do is take pre-trained parameters and add a smaller, less dimensional matrix to train it. So it's less complex and it's more resilient and can be integrated into pre-existing neural networks easier. So for our project, we utilized LoRa to fine-tune parameters for a separate GPT-2 model using weight matrices. Our goal was we wanted basically we gave it a data set containing a bunch of medical conditions and the associated drugs to treat those medical conditions. And we wanted our model to be able to, if you were to give it a medical condition, output a made up potential drug based on the pre-existing patterns. And so
So yeah, so we are able, using LoRa, we're able to like take the data set and fine tune the parameters such that we are able to, like Sophia was saying earlier, create a lower dimensional matrix that we are able to feed into the GPT-2 model. And then here's how we like tokenized our data. So this is kind of really difficult to do, guys. It kept on like, it was weird with like mismatching set sizes because it wanted one thing, like the trainer wanted one thing, but then the tokenizer was like, no, and then it wouldn't give this thing that I wanted. So like bounding that was pretty difficult, not gonna lie. But we were able to like tokenize it into like medical condition, drug. Most of the time it did produce novel names, whoop whoop. So for example, the the cure for death is Ishmael Coldfingers. You guys haven't heard of it, now you have. So it would produce most of the time novel names for medicines that could treat the condition. However, sometimes it would give like pre-existing names, like for example, lupus, acetaminophen, ibuprofen. Don't take those two drugs, guys. I don't know if you should mix those. Maybe you should. I don't know. I'm not a medical professional. However, there's room for improvement. Like maybe next time, like train it for more epochs and like train it for longer, I guess. And also for future projects, maybe like also provide novel side effects, like your fingers will grow trees out of them. I don't know. But yeah, so that was our project. Is there any questions on our project?
There's our project.
Hi, Vic.
Thanks. Okay, so for my project, I wanted to make a model which would take in a database I got on Kaggle of a bunch of posts from different politically leaning subreddits and see if I could ask it to create like sort of sample posts that you might see there based on political leaning. So I used PEF to do most of the LoRa work. And yeah, so here were some sample responses. It definitely has a long way to go, but I was pretty happy that it was creating stuff that wasn't directly just like stolen from the database. And there seemed to be at least some differences between them, like they seem to actually be properly sort of associated with political leaning and whatnot. So reflecting on my project, I guess what went well was sort of like what I just said. The responses were distinct, and it did feel like it was like learning every time I ran the training loop. So maybe if I ran it a little bit more, it would be better. But difficulties, there are quite a few. This was my first time doing something like this. It was not very well optimized at all. It took way longer than I think it should have based on what it was being trained on. And I had to change which model I used. I think I used Distill GPT-2, but originally I used Gemma, which was not good. I ran out of RAM. The computer also like really limited the size of the data set I could use, so I only was able to use a subset. I think maybe if I used more, answers might have been better as well. So for improvement, I think obviously I could have made it look at a little bit more data instead of being limited in size. I also maybe want to make it able to answer questions that are not just like generate a Reddit post, but like, you know, answer this with like liberal or conservative leaning. And then also introduce more nuanced political leaning besides just conservative and liberal.
Is there any questions for anyone doing Transformers? Cool.
Okay, if we could have Debugger Lab come up now.
So try to hold the mic slightly below your mouth.
All right, hello everyone. We're Debugger Lab. I'm Jason.
I'm Isaac.
Okay.
I'm tired.
I'm Isha.
I'm Lena.
I'm Daniel.
I'm Alex.
I'm Nathan.
I'm Diaz.
So yeah, just very quickly, like the background and motivation behind this lab. We're making a debugger to analyze and inspect processes, sort of like how GDB works. Currently we only support x86 Linux, and we have a lot of features implemented that you would expect from a debugger. So you can read and write registers, you can read and write memory, you can set and unset breakpoints. The screenshot on the right doesn't have, you know, unsetting breakpoints or writing stuff, but just trust me, we have it. We have a lot more advanced features that we'll be talking about on later slides. GDB does a lot of really cool things behind the scenes, so it was really cool working on this lab. You know, having a debugger helps with debugging. Wow, I know, crazy. Reverse engineering, right? So if you have a program and you want to figure out what it does, being able to step through it is really, really helpful. And it also helps with like binary exploitation. If you have a vulnerable program with a memory corruption exploit, it really helps to be able to see why your vulnerability is or isn't working.
All right, so one of the algorithms that we implemented is the backtracing algorithm. So backtracing is a very useful debugging technique that involves printing the call stack of a program at a specific point in time, and this is usually during a program crash. So this helps several developers to trace back the sequence of function calls from the current function and back to the main method that kind of led to the crash or unexpected behavior.
Yeah, so how backtracing works or how we implemented it was we just read from the register base pointer and used ptrace to access the address in memory. And then from that, we got the previous frames, register, base pointer, and return address. And just by following the chain of base pointers, we can step backwards through the call stack frame, and it ends basically it ends by reaching an invalid address in memory, and that's when you know you reach the end of the call stack.
So another feature we have is reusable breakpoints. So obviously, if you have a debugger, you want to be able to stop the program execution at a certain point and analyze the program state, and you can do that through breakpoints. So the way that a breakpoint works is it's basically going to replace one of the machine code instructions with the instruction like OXCC, and this sends a breakpoint interrupt, and that basically causes the program execution to halt, and then we can analyze the program state. But when we resume execution of the program, we want to have the original machine code instruction, we want to restore it. So we have to restore the instruction, right? But then that removes the OXCC instruction and we no longer have a breakpoint. But this is problematic if we have important segments of code that were repeating, like in a loop or a function that's called multiple times. So to solve that problem, after you exit the OXCC instruction, you step forward one instruction, then you rewrite it with the original instruction that was still there, and then you resume the program execution, and that allows you to have a reusable breakpoint instead of one that expires.
Okay, so the next feature we have is disassembly, and this is like very similar to if you've done like CS33 or yeah, the CS33, CS111, I'd say. Like object dump dash D or disassemble GDB. You want to see like what instructions you have currently in in your program so far. So how does that work? You have like instructions stored in your ELF file or your program, your compiler program as like hex digits. Well, really it's stored as binary, but you can represent it as hex digits. You can parse those hex digits with this thing called capstone, which is called a disassembler framework. Capstone does much of the heavy lifting for us, and it'll just parse our hex from the memory, which we got with peak text from ptrace, and then we just get an instruction. We get where the instruction ended because instructions have variable lengths in x86 64, which is so fun. And we can then read the next hex digits in memory to get our next instruction. Then we repeat this process. Cool.
So we did some ELF parsing. ELF is executable linkable format, which is how Linux binaries are stored on disk. So we parse the ELF. There's some technicalities over here, but the main idea is that we collect the symbols, right, from the symbol table as well as the dynamic symbol sections, and basically allows for you to like print the symbol and break on the symbol. Yeah, and then I'll let Nathan explain the dwarf.
Okay. So ELF was an acronym that they just like happened to come up, and so they decided it would be really funny if we named the debugging symbols dwarf. So they tried really hard to make the like acronym work out, which is why it sounds dumb. Yeah, basically dwarf contains debugging info. There's a lot of technical terms here, but basically, one thing that's contained in the dwarf info is detailed stack frame information on every single function. So if you remember from before in the back tracing, we read RBP to find the frame pointer and then we walk up the stack. But this doesn't always work. Sometimes compilers will elide pushing a new stack frame because it takes time at runtime in order to do so. So parsing dwarf allows us to do more precise backtracing. And hypothetically, in the future, we could parse it to get variable names like that.
Yeah, and we also added support for PI, which is position independent executable, and also shared libraries. So after the child process finished starting up, we can get its PI base and other very important information from the auxiliary vector. And on Linux, it is exposed as such proc/pid/auxp. And then we can find the address of the DT debug structure in the dynamic section, which is essentially the interface between the dynamic linker and the debugger. And through using that structure, we can iterate through the link map to obtain information about each loaded library. And as you can see on the right, the picture on the right here, we run the debugger on bin ls, and it's a dynamically linked executable. So you can see that it uses 3 shared libraries, and we collect basically add all 3 libraries, and we're able to break on the right function, which is a function inside of libc. So you can see it has a higher address, and then we can continue. You see it prints out the first line and the second line, and then it exits. So take this.
Yeah, I guess any questions before we go? Okay, so we're now gonna have our intermission. But I don't know, maybe some of you guys saw the whispers of this in our Discord channel, but it is a very special intermission. So we have something of a tradition of pieing the previous C-Prezes. This started off because one of our C-Prezes kept meetings going late, and so for each one of those, there's a one pie. We are pleased to say that our past C-Prezes did not commit such heinous sins, but they're getting pied anyways. So, if you'd like to join us all outside, since we should not have whipped cream inside here. Yeah, I guess we'll just head out to the patio, I suppose.
Yeah, it's right at that door right there.
All right, let's get moving. All right, we'll be starting back up again. So if you could all take your seats and if you could have your attention. So we're gonna hand it off to some of our PBR directors now.
So hey there, I'm one of the 3 PBR directors this quarter for Cy Beta Rho. If you don't know, Cy Beta Rho is our competitive CTF or capture the flag team here at ACM Cyber. And let's just say this quarter we kind of won big. So if you let this animation play out slowly, this quarter we won a lot of money actually. We got some pretty high placements. We got in second place student division, we got at Squirrel CTF, we got second place student division, which is $150 of prizes. And then probably our best result this quarter, we got first place at Boiler CTF, which is actually our first place ever that our team has ever accomplished. So definitely congrats to the entire team for that one. And that is 600 buckaroos of dollars right there that we got. And finally, we got another second place at San Diego CTF. So thank you, other ACM Cyber at UCSD for running SDCTF. Thanks for the $128. Yep. So yeah, we kind of won big this quarter. And you know where all the money's going? That's right. It's all going into the ACM Cyber. Oh no, our funding's been cut fund. So yeah. But yeah, without further ado, I'm gonna hand it off to Arnav, who will be giving a live write-up of a challenge we did at Boiler CTF.
Hey everyone, I'm Arnav, and I'm going to be giving a live write-up for What the Crypto. It's a web challenge from Boiler CTF. This challenge had 15 solves, and we got both the first blood and the first write-up, the write-up prize for this challenge. As you can see in these pictures, there's some images of us frantically trying to get the blood, like trying to solve the challenge as fast as we can before we have to leave the room. So what does this challenge have? It has, first of all, a simple login endpoint where we can enter a username and a password. When we send these in, we send a post request with this data to the backend. Then the username and password are checked against an allow list of characters. These characters are A to Z, the underscore, and the open and close braces. So as long as our username and password consists of only those characters, it's allowed. Otherwise, it's not allowed. And then afterwards, both of these are encrypted with AES CBC. Once the encryption happens, we then redirect to this link, which is you kind of just have a URL parameters of our encrypted username and our encrypted password. Then this endpoint will decrypt the username and password with the same key and uses these decryptions in an SQL query, selecting from the users table where the name is our username and the auth secret is a password. So it's just looking for the correct username and password combination. And there's 3 possibilities when we run this. If the username and password combination is found in the database, we'll output that user and we log in successfully. If it's not found in the database, we output like login failure, incorrect user, or something like that. And then if there's an SQL query error, it will be a third different output, which just says error, no other additional information. So how do we get about to solve this challenge? At first glance, this looks like an SQL injection because there's a very, very simple like SQL query that we can kind of control what gets input to it, and maybe we can kind of cause an injection. But the problem here is that we need a valid encryption of our payload. Whenever we send something to the login endpoint, it gets encrypted and then gets decrypted and then used in the SQL query. So we need an encryption. The only encryption oracle is posting to the backend, which encrypts for us, but it has an allow list and it blocks anything that's not in the allow list. So how could we bypass this? For an SQL query, we want a username or password that looks something like that with all these extra characters like the quotation mark or the equal sign or whatever? How are you going to be able to do this? So some people may think that just by encrypting something, if only two people know a key and one person encrypts the data, only they could have created that encrypted data, and thus we can trust them. Some people might think that. Well, this is not true, because if we kind of when we do the redirect to the username and password, we can change what the encryption of the username and password are. And if we change them correctly, we can kind of affect how they get decrypted on the back end. So the mode of operation that they use for AES is CBC, where previous ciphertext blocks are XORed with current plaintext blocks before encryption, which means that before anything happens, first we XOR the IV, we encrypt the first, we XOR the IV with the plaintext, then we encrypt. Then we take that ciphertext, XOR it with the next plaintext, and encrypt, and keep going like that. The IV is like 16 bytes that kind of starts off our encryption. These are added alongside our actual encrypted username and password, and we can modify it to whatever we want. So as you can see, if we change 1 byte or we flip some bits in the IV, we can affect the same exact bytes or bits in the plaintext in a very controllable manner. So we can kind of make the first plaintext whatever we want. And this bypasses the filter because the filter isn't checked after we do the redirect. So how exactly can we leverage this? The flag that we want is located in the auth secret column of the users table for the user admin. So we want to recover what this flag is. And we can use this kind of payload for SQL injection, which results in that query. What that query does is basically it searches the table and it checks if there is an auth secret that matches that like wildcard, which is star test star, where test is like a known substring of the flag plus 1 single guess byte. So what we can do is basically start with what we know the flag format is, which is, I think it's BCTF open brace, then guess 1 additional byte in the next position. Once we get that byte correct, we can move on to the next position and guess that one and keep going until we build up the entire flag. This is basically a binary oracle because if this query succeeds, we get a different response from if it doesn't find anyone. But the problem is that the payload that we just saw is too big to fit into one AES block, which is 16 bytes long. So just by modifying the IV, we can only affect the first plaintext block. How can we control multiple blocks to have longer than 16 bytes of a query? Additionally, a caveat is that if you modify one ciphertext block in AES, it'll completely mess up the corresponding plaintext block, but it will allow you to control the next plaintext block. So this is maybe something that we could use here. We basically can alternate between plaintext we control and junk plaintext. And whenever we have a junk plaintext, we want to comment it out to prevent anything weird from happening. So as you can see on the right, now we've circled the second part of the AES decryption, and we change one part of the ciphertext. The current plaintext will get completely messed up, but we can specifically control the next plaintext. So now we can just keep abusing comments like this. We can modify blocks 0, 2, 4, 6, where 0 means the IV, where that means we can control blocks 1, 3, 5, 7 in the plaintext. And then all the other blocks that we don't control in the plaintext, we just comment them out by surrounding all of our controlled plaintext blocks with these comments. So this is kind of like the structure of our query or our payload. And now each part of this fits within a 16-byte block. So this is basically how we get the flag. We kind of build this query that uses the encryption, and we modify certain parts of the ciphertext so that when they decrypt, they change to a different query that lets us like recover the flag byte by byte. The only problem here is that once we modify these parts of the plaintext, there's a somewhat significant chance that we get a null byte in the decrypted plaintext. Even though we are commenting this part out, the null bytes will still mess up the query because SQL doesn't like null bytes. So this will cause an error in SQL, and this will result in what mostly happens is that it matches a wildcard character instead of the actual character when we are exfiltrating the flag. So the solution to this is by running a slightly different query. If you just slightly change one of the words in the query, you'll be fine. So instead, of using glob, you can use like and build a very similar query, but it'll kind of fill in these holes where there were null bytes. And that's basically how we solved the challenge. Any questions? All right, if we could have the Kaggle group come out now.
Microphone. Hello everyone, this is Stanford RNA Folding Capital Group. My name is Cham.
My name's Clark.
My name's Luke.
Name's microphone. Use microphone?
Yeah, let's use the microphone.
Okay.
So what is RNA folding? So RNA folding is the process by which an RNA sequence forms a 3D structure through base pairing and interactions. But we have a lack of data towards that. So we're trying to find out the sequence of the RNA by like 3 parts, which is their nucleotides, their base pair interactions, as well as their 3D conformations.
Yeah, so basically all deep learning based ways to solve the RNA folding problem or any folding problem is the same as AlphaFold, which was the model that solved protein folding. So AlphaFold basically consists of 2 major pipelines that process the information, which is the pair representation and the sequence representation. So the sequence representation captures and processes information about every individual amino acid. In this case would be, since we're doing RNA folding, would do every individual nucleotide. And the pair representation captures information about pairwise interactions between amino acids. This part is necessary because like in 3D space, if you have like, for example, if you have like the pairwise distances between all points in a point cloud, you can get a unique point cloud most of the times. So that's probably the reason why they used pairwise interactions. So these paths also exchange information between each other as the information is processed. So how does each path actually process the information? So obviously the attention mechanism, because transformers are just cool. And we do have to obviously modify our attention mechanism because we're using pair representations, which is a matrix instead of a sequence. So we do this by treating the pairwise representation as a complete graph on all n nodes, where each node is a amino acid, or in our case, a nucleotide, and doing stuff with triangles, which is it's kind of complicated, I think. The reason why they do these things is to help it learn the triangle inequality. That's it. Intuition. Okay.
So what our competition was about with RNA is to predict the 3D structure of RNA molecules from their nucleotide sequence with machine learning principles. Why does it matter? Well, RNA is ribonucleic acid, and as we know, it's in like every part of life, like plants, humans, viruses. RNA also is very important in producing proteins, and these proteins have different functions in our biological system. So we want to like find out the key in understanding the gene expression of RNA and the design of it, it is also significantly harder than protein folding because we have less data than it. And our challenge is to specifically accurately fold RNA sequences into 3D conformations with machine learning, of course. So what we got out of this are metric learning. Oh, you want to? Sure, go ahead.
So the competition gave us this one metric, TM score, which is like, all you need to know about it is that it like measures how well a structure is aligned with like the target structure. So like you can see on the diagram on the right that if you have a structure that looks pretty similar to like the one that you want, then you get a TM score that's high, and then otherwise you get a TM score that's low. That's pretty much all that matters. The reason why the competition actually lets us submit up to 5 structure predictions for each actual sequence. The reason why this probably exists is because sequences can have isomers. So like you have one sequence that can fold up to like many possible ways. So you want to like give the participants a way to like have diverse predictions so that if one of them is wrong, then maybe another one is right. So then you like mitigate the risk. Right. So one issue we faced just going into the competition is that they gave us only around 900 structures. And if you know anything about machine learning, like this is definitely just not enough data to actually train a model from scratch. There's many open source RNA folding models all around, and there's obviously this is like the new frontier of, I think, folding research after like protein predictions were solved. So then you have all these models, and they've already been trained by all these researchers. So like might as well just use them, right? But then the issue with all these models is that these are like they're like very poorly coded. They use like floating point 64. They have memory leaks all over the place. You can see like they implement einsum. Wait, you want to explain this?
Yeah. Does anyone from the audience want to know or know what's wrong with this line of code? Okay. So the issue here is that since it's doing a mean over the n dimension, there's no point in storing the entire sequence length inside the einsum. You would just get rid of the n here and then divide it by the length of the sequence. And this just makes the memory like n times larger than necessary. I don't know why they were, I guess biologists should just stick to biology, man.
Okay, so yeah, so our approach is just, okay, let's just take one of these models, let's ensemble them in a way, and then let's hope to get a high score. So this is our 3-step method. Let's take 6 off-the-shelf models. Let's run them on the train set, and then since we know like the actual structure, we can calculate the score that each model gets for each candidate prediction, and then we train a meta model that sort of takes in a structure, takes in the sequence, and outputs what's the expected score for this structure, right? And then we can just form a ranking of, oh, this sequence looks to be a pretty good answer, so then we'll submit this as our top 5. Yes. So here are the model details. There's nothing too significant like about these models. All you gotta know is that like they use like relatively diverse ways of folding them. Some of them follow AlphaFold, which is like you start all the points at 0 and then you just like iteratively refine them. Some of them do a sort of diffusion process where like you add noise in between the steps. Some of them restrict the restraints between points, so like how big an angle should be or something like that. All you gotta know is that it's a very diverse set of models, and this is good in ensemble. So essentially this is what we did. We ran the models on the train set, we collected their outputs, we created a model, like a pre-trained model that just predicts the score of each structure. And then we also trained the RL model to like pick 5 out of like 20 structures. And this is like the reason we did this is because like you have a potential model, you have potential structures where like they're all the same structure,
So like they all have like a high score that it could be, but like you want a diverse set of answers so that like if this structure is not correct, then maybe another structure will work. So this is what we did. We got a cross validation score of 0.4 on the train set, which if this translated directly to the leaderboard, this would be like a silver medal.
Unfortunately, our final notebook did not actually do it properly because we ran out of disk space for some reason. Whoever implemented the Dr. Fold notebook just did not clear the intermediate step. And I guess they were just like edging it with the memory, and like combined with our notebook, I guess we just used too much disk space. This is actually kind of stupid too, because like we could have used like the Kaggle temp directory. So that was on us. We should have like submitted a couple days before the deadline, but that is what it is. Here's a 3D structure that I rendered in Blender of an RNA molecule, if anyone's interested. And that's about it. Any like RNA folding, like how I can technically it's easier. Like there's like around 20 above, I think it's more than 20 different amino acids, while there's only like 4 nucleotides. So like that just makes it
I don't know.
It's also like easier in terms of like if you're thinking about it from like a pure biology perspective, because like there's only like two different secondary structures, or 3, I guess. I don't know, because like if you can count the pseudoknots, but it's the only issue is the data. Like amino acids have, I think there's like a million before AlphaFold, so that's why they were able to actually solve the problem, whereas there's not enough for RNA. Yeah, yeah. It's not only the mRNA. There's also something called the ribozyme. So
Yeah,
RNA can also be like how proteins can be enzymes. RNA can also catalyze different reactions. That's why the 3D structure is important. If that answers your question. All right. Let's give them another round of applause. Okay, if we could have the ECTF team come up. Round of applause, please.
Oh, he's getting the food.
What if you Yeah, so quick recap. So the competition ended earlier this quarter, and we were able to place 8th overall nationwide. So there were over like 100 colleges competing. So yeah, I think we can say we did pretty well. And we went to the awards ceremony to present to some of the other teams and get to network a little bit. So have some nice photos here. And since the place was in Boston, it's known for seafood and lobsters. Sorry, AI, you're very tasty. Yeah, okay. So just a quick recap of the competition scenario. You don't need to worry about all the intricacies of that diagram. Basically, you have data like TV frames, and so you only want people who have paid for a subscription to be able to see it, right? And so starting off with the raw data, you can process it using an encoder, then it gets sent over to a decoder, and then that'll do something, and then either show the data or say like, hey, you don't have a subscription. And so if you just send the data in the clear, then
obviously anyone can look at it without even needing a subscription. So the idea is you want to encrypt it somehow, right? Now this is easier said than done. We were actually one of the teams who, well, the way this works is that you create a design and then other people try to attack you and you try to attack everyone else. We were one of the only teams that did not get any of our attack flags captured, so we had a perfect defense pretty much. But I guess we have some attack highlights which show that well, not everyone was able to do this.
So I guess the first tech highlight is some pretty basic crypto fails. So one pretty funny fail was just people leaving their keys in the attack package. So we were like looking at this a few particular teams, and then we just happened to see a secrets.h with just all of their like with all their leaked keys, as you can see over there. And yeah, as a rule, do not give the public your secret keys. Also, another thing that we noticed a lot of teams doing was just like reusing stuff that's not meant to be reused. So in cryptography, there's this concept called like an initial value or a nonce, and like I guess like from the name nonce, you're supposed to use it once. But a few teams did not use it once; they use it many times, and I guess with certain ciphers like AES GCM, if you like reuse a nonce, you can kind of just like do a lot of very funny things. Yeah.
And there was many more other crypto fails as well. So some people may claim that encryption and authentication are the same action in cryptography. I can prove to you that I created a piece of data by showing you its encryption, but this is not true, as we will see. This is not the case. So first of all, encryption is not equal to authentication. And what happened with a lot of teams is that they used ciphers like AES ECB or AES CBC, where we could basically modify parts of their ciphertext to modify different parts of their plain text to cause weird behavior to happen and eventually leak flags. This is a very common attack, kind of attacking AES ECB, AES CBC like that. But then even with teams that did try to implement authentication correctly, some teams just did not check the authentication tag. As you can see, they got a result, but they just returned 0 and ignore the value of result. And then some other teams tried to be really fancy with their crypto systems. They tried to home roll special crypto systems that provide encryption, authentication, and just are very secure in general. So one team made this crypto system called Tai Chi, which stands for Totally Asynchronous Interval Cipher for Honesty Identification. As you can see, the S in this acronym stands for secure. It was not secure.
Okay, we also did some side channel attacks this year, which was pretty exciting. So there were multiple teams where they were using a function called like memcomp, which is just memcompare, to like compare like signatures. So like the idea is that the signature value here is like something that we input, and then like computer sig is basically like a 32 byte like 32 random bytes that like we don't know, and like in order to pass this check we need to like get the two to match. So like normally you cannot like guess 32 bytes because that would be like 256 to the 32 possibilities, which is like astronomically big. However, the thing is memcomp is this working? Yeah, okay. Memcomp is not constant time, so this means that like it basically like converts it compares like each byte between like the signature and computer sig, and it will like stop as soon as it finds a byte that doesn't match, which means that it takes slightly longer if we have like more bytes that are correct. And this team, they happen to have like this LED color change that's like right after this verified signature check, and they also have like an LED color change that's before it. So if we measure the time interval between those two changes, then that allows us to precisely measure the time it took for this comparison, and that tells us like how many bytes we got correct. Yeah, so we using some like specialized hardware called Chip Whisper and some like extremely janky wiring to like probe the tiny LED here. So we could like measure the difference, which is like around like a couple hundred nanoseconds. So what we could do then is that we could like try all the 256 possible values for like the first byte and then see which one took the longest, and then we know that that one's probably the correct one, and then we just repeat that for the second byte and so on. So instead of like guessing like 256 to 32 possibilities, now we just have to like make 256 times 32 guesses, which is way less.
Some other like funny attacks that we found during attack phase include like just traditional buffer overflow attacks. So in the starting code given to us by like Meter, who like runs the competition, they give some starting code. There was actually a buffer overflow that kind of spanned three functions where like they allocate a buffer in one function and then like three calls down the function or three calls later they actually use that buffer without like worrying about how large it is. So a lot of teams copied that code and had interesting buffer overflow attacks. Here's kind of an example where teams would like write a packet with like a frame size that you could like the same frame size as you sent over the network. And so if you just like told it that your frame was going to be like 10 billion bytes long, it would just dump 10 billion bytes of memory over the network. And if you did not have a secure crypto implementation, this means that you could actually leak like keys off the device, which is pretty cool. The other thing is a lot of teams left in some debug prints that were pretty interesting, such as like for example, if the HMAC doesn't match, well, we'll just print out the right one for you, so you can use that in your next attack against us. Pretty helpful, I will say, for an attacker. So yeah, a lot of teams left in debugging information and LED information that's useful for timing attacks and other cool stuff. But yeah, that was basically all we did this year.
Any questions? If not, then give the team a round of applause. And then if we could get the AI mini ML and the reading group to come up.
So earlier this quarter, we hosted our very first mini ML challenge, which was basically a 4-hour mini hackathon where people were able to do like a mini image classification task in a group. So here are some photos from the event. We got pretty good turnout considering this was like our very first time putting it on. I think we encountered a couple technical bugs just with like making the competition a bit too advanced. We didn't assume people were going to be like from scratch beginners, but I think we're going to take that and learn from it next time we try to put this event on. So here are some of our winners. I can explain the tracks that we had. So for the beginner track, we basically had this data set consisting of Minecraft biome images. And what we did is we converted them to grayscale and also like cropped and like clipped the images so that it would make it harder for participants to train their models to classify an image with a particular biome. So then after that, we were able to have participants submit to a Kaggle notebook, and then they were able to receive feedback based on how well their model was performing on that unseen testing data. And for advanced track, which Lawrence is going to explain what he did for that, it was also image classification, but with a far larger data set of satellite images.
Okay, yeah. So basically the goal was to train a small model, so less than 100K parameters on satellite images to recognize different whether it was like forest and like desert and things like that. However, because we didn't want to bother with actually doing hyperparameter tuning for such a small model, we just used knowledge distillation. So we fine-tuned a larger teacher model on a data set, and we used the output logics from that to train a smaller model, which is a little bit cheating, but no one told us we couldn't do it. So yeah. So the larger model was just the off-the-shelf ResNet 50, which we fine-tuned on the data set. That achieved about 90% validation accuracy. We never actually got our test accuracies back because there's a little bit of a bug with the actual grading notebook. For the smaller model, it was a custom ResNet-based CNN with around 65K parameters, and this got around 85% validation accuracy. For implementation details, we use Hydra for the conflict management and PyTorch Lightning because we are lazy and we didn't want to write any sort of actual code. And yeah.
Hello. So unfortunately, this quarter we were only able to host one reading group because I mean spring, right, guys? So yeah, and the one that we did do was on parameter efficient fine tuning, and it's by Lawrence as well. So I made a little joke about regarding parameter efficient fine tuning methods, like why did Laura break it with Galore? Because Galore said it's not you, it's rank. I just need subspace right now. You know what I'm saying? Yeah. So the parameter efficient, of course, yeah. For parameter efficient fine tuning, you have like a gigantic pre-trained model, and you have so many like billions upon billions of parameters. Like it's prohibitively expensive for you to actually just like fine tune the entire model. So there are a lot of heuristics about like what you can do in order to fine tune it without updating the entire all of the parameters. So one method would be like LoRa and QLoRa, low rank adaptation. But these make a lot of assumptions about the nature of the update weights. Like for example, LoRa assumes that the weight delta is like inherently like low rank, which is like not necessarily always true. And the example that Lawrence gave prior was regarding the fact that like regression is not inherently low rank. And also there was something towards the very end of the presentation regarding this technique called Galore. And instead of assuming that the delta, the weight delta is inherently low rank, we can prove that the gradient is actually low rank, and we can project that into a subspace chosen with SVD, singular value decomposition, and perform atom on that instead, and then project it back into the original space. And then you can do kind of better than that because for some reason, I'm not completely sure why, but when you choose the top subspaces, it turns out that you just can't optimize along the same directions, and that's actually as time progresses, that becomes worse and worse at fine tuning. So if you just like randomly choose, you just randomly choose subspaces to project into, it turns out that that actually gives you better fine tuning performance. Yeah, so and then the next slide is just going to be the pictures that we took during that reading group. Thank you.
All right. So thanks for coming, everyone. Before we do food, if everyone could come up here for a quick group photo.